Electronic waste, commonly referred to as e-waste, sets itself apart from waste in general due to its unique chemical composition. Aside from hazardous materials, e-waste contains noble metals that require special handling and care. Moreover, copper, a widely used metal in electrical appliances, contributes to a staggering 82,000 tons of global emissions. It is estimated that the production of electronic devices accounts for roughly 67% of all carbon dioxide emissions into the atmosphere. Between 2014 and 2022, emissions associated with electronic waste increased by 53%, underscoring the pressing need for effective recycling methods in this domain. Recognizing this urgency, Green Electronics comes to the global stage of progress. To develop an electronic device, it is necessary to start from its smallest building units, transistors. Although they have not yet reached the level of miniaturization seen in modern integrated technology, these transistors, known as organic field effect transistors, yield promising experimental results. Additionally, organic light-emitting diodes (OLEDs) play a crucial role in this context. Significant alternative biodegradable and biocompatible materials such as gels, fibers, films, sponges are being considered as substrates for functional units in nano and microelectronics. Finally, the primary focus of the Greenelit project centers on a specialized facet of green electronics, edible electronics. With the growing interest in precisely detecting irregularities in occlusion, as well as correcting them as soon as possible, bite force sensors have been an avenue of interest in the biomedical and dental communities. Our team of researchers has pioneered a groundbreaking method for measuring bite force. The newly proposed and developed bite force sensor not only fulfills the requirement for a functional and highly sensitive sensor, but also boasts a unique feature. Its transducer is crafted entirely from an edible hydrogel, making it biodegradable and biocompatible. To illustrate its functionality, our researcher employs an occlusator as a demonstrative tool to showcase the sensor in action. As the force applied increases, there is a corresponding change in capacitance. Edible inductors contribute significantly to reducing electronic waste and promoting the development of more sustainable technological solutions. Creating devices that are safe for human consumption offers numerous advantages, including biodegradability, non-invasive monitoring of physiological parameters, and secure integration into food packaging for quality monitoring, among other benefits. After fabrication and about 24 hours of drying, the edible inductor reaches stable physical properties, and electrical characterization can be performed. Electrical characterization includes measurement of electrical impedance modulus and phase angle, as well as estimation of series inductance, the self-resonant frequency, and the quality factor. Our manufactured inductors are compatible with standard impedance analyzers' input ports, requiring only device configuration. Exploring electrical characteristics across a wide frequency range is of interest, as it allows us to identify the frequency range where the inductor has the best performance. In the last few years, a significant number of researchers and research teams have shown interest in the field of edible electronics. This increased curiosity has led to a surge in both research initiatives and the number of scientific papers. Still, a large number of edible electronic components are not completely biocompatible and biodegradable. We have shown that completely edible and biodegradable substrates can be made from food residues. These substrates can be utilized for the fabrication of functional electronic components that are also completely edible in a simple and fast process. We have developed a procedure for the production of simple electronic components using materials obtained from orange peel, grapefruit, lemon, apple, banana, kiwi, potato, carrot, cabbage, and eggshell. Initially, the materials underwent dehydration, followed by a pulverization process to achieve the finest powder possible. Then, they were interconnected using various natural adhesive materials, including honey, sugar, starch, and gelatin. The ultimate goal was to develop functional electronic components from food waste for application in biomedicine. Reliable measurement and acquisition of physiological parameters is among critical tasks in human health monitoring. During the past period, considerable efforts have been dedicated to creating devices designed for personalized electrocardiography (ECG) and electromyography (EMG) measurements. The existence of these devices allows for increased data collection, enhancing health monitoring, but it also results in a greater usage of electrodes. On the other hand, commonly used AG/AGCL electrodes are not free of charge or biodegradable. Therefore, their extensive use leads to higher costs and higher waste production. We created ECG/EMG electrodes using biodegradable materials, specifically two types of potatoes, Solanum tuberosum and Ipomoea batatas. We performed successful integration of potato peel-based electrodes with the commercial device, BioPack Acquisition Unit. Observations from 8 healthy volunteers showed minimal variations when extracting heart rate, inner beat interval, or normal to normal intervals from the ECG signal using potato peel-based electrodes compared to commercial AG/AGCL electrodes.
We expect that green electronics in the future could serve raising needs that we have. It's quite difficult to think that we are really replacing electronics for supercomputers, right? It's going to be there because we need extremely high performance. So this sort of green electronics might replace some parts of that, casings and wirings, but not the core of the computation, which is going to be silicon. But there are other needs. So electronics is going everywhere. Electronics is going in wearables, in healthcare. So in that case, where you probably don't need such extremely high performance, but you need other properties like large area, bendability, flexibility, durability, compatibility with soft tissues, then I think green electronics has a place there in the future.
EU funding, you have to, build consortiums across borders, across disciplines, so it also enhances knowledge migration and knowledge utilization between different groups and different key knowledge bases in the EU. Also, I feel it's fantastic that in a consortium like the Greenelight consortium that we had the opportunity to meet different people, start different projects like this new EU-funded project with Novi Sad.
This area of science is new for this region, and our institution will be a leader for this part of Europe in this field, thanks to this project and thanks to the European funds for this action or this program.